So let's suppose we have the following system of four objects that is in static equilibrium. So we know what the mass of object B is. It's simply 0.75 kilograms. And we also assume that beam number 1, beam number 2, beam number 3, as well as these cords are all massless. So knowing that and the given information, we want to calculate the mass of object A, object C, and object D. So we break our problem down into two steps. In part 1, we're going to calculate the mass of object C and object D, and then using that information and the given data, we're going to calculate what the mass of object A is. So let's begin with step 1. Determine mass of object C and object D. In this step, we're essentially examining beam number 2 and beam number 3. So let's begin with beam number 2. Beam number 2 is shown here. So to one end of the beam, we have object B connected, a distance of 0.05 meters from the rope, and we choose the rope to be our axis of rotation. Now, from the axis of rotation to where objects C and D are connected is 0.15 meters. And notice, because these ropes are massless and beam number 3 is massless, then that means the total sum or the total mass connected to the other end, to this end of beam number 2, is simply the combined mass of object C and objects D. So this beam as well as the objects are in static equilibrium. That means the net torque acting on the beam is 0. So we choose the clockwise direction to be negative and the counterclockwise direction to be positive. So we have this torque, which is due to object C and object D, minus torque due to object B is equal to 0. So we rearrange this equation and we see that torque due to object C and D is equal to the torque due to object B. Recall that torque is equal to force, which is in this case the force of gravity, multiplied by the lever arm, the perpendicular distance from where the force is acting to the axis of rotation. So we get mass, or the combined mass, of object C and D multiplied by the gravitational constant G multiplied by the lever arm from the axis of rotation to where these two masses are hanging is equal to mb, the mass of object B, which we know, G, our constant, multiplied by the lever arm dB, beginning at the axis of rotation and ending in this position. So notice that the G's appear on both sides. That means we can cancel them out and we get the following result. Now we know what this, and this quantity is, and that means we have to solve for mass of object C and D. To find the mass of object C and D, we simply rearrange our equation. We get the following result. We plug in our values. So mass of object B is 0.75 kilograms. The lever arm from this position to this position is 0.05 meters, and the lever arm from this position to this end of the beam number 2 is simply 0.15 meters. So we plug those quantities into our calculator and we get a combined mass of 0.25 kilograms. So next we move on to beam number 3. So beam number 3 is shown here. So the same exact procedure is done for beam number 3. We choose the axis of rotation to be at this position. Mass D is hanging a distance of 0.05 meters away from axis of rotation, and mass C is hanging a distance of 0.175 meters from the axis of rotation. So once again, because our beam number 3 is in static equilibrium, our net torque on the beam is 0. So our torque due to object C minus torque due to object D is equal to 0. Torque C is equal to torque due to object D. And recall once again that torque is equal to force acting on the object multiplied by the lever arm. So we have mass of object C multiplied by G multiplied by this distance is equal to mass of object D multiplied by G multiplied by this distance. Once again, the G's cancel and we're left with the following result. Now, notice we don't know what MC is and we don't know what MD is. So we have one equation and two unknowns. So that means we can't actually solve this equation, and instead of solving, we're going to find the ratio. We're going to calculate the ratio of mass D to mass C. So that's equivalent to the distance DC divided by DD, where DC is simply this distance and DD is simply this distance. So 0.175 divided by 0.05, that gives us 3.5 to 1. So the ratio of mass D to mass C is 3.5 to 1. So to find the rate or the mass of object D, we simply take this quantity, 0.25 kilograms, and multiply it by 3.5 divided by 4.5, where 4.5 is simply 3.5 plus 1. And we get approximately 0.19 kilograms is the mass of object D. What about the mass of object C? So now we take this quantity and multiply it by 1 divided by 4.5 and we get approximately 0.06 kilograms. And this is the mass of object C. Now, we could have also determined the mass of object C by simply taking the total mass and subtracting the mass of object D. We would have gotten the same exact value. Now let's move on to object number A, or object A. What exactly is the mass of object A? So, now we're examining this entire beam. So this entire beam is drawn in this section. So once again, the chord, the massless chord, acts as the axis of rotation. The distance from the axis of rotation to where object A is hanging is 0.3 meters, and the distance from the axis of rotation to where all these three masses are hanging, so mass B, C, and D, is 0.075 meters. So once again, we assume static equilibrium, so that means the net torque acting on the beam is 0. So that means torque created by object A is positive, and the torque created by the combined mass of object B, C, and D is negative. So we take the sum, equate that to 0, rearrange the equation, and we see torque A is equal to torque B plus C plus D. So once again, torque is equal to mass of that object multiplied by the gravitational constant G multiplied by the perpendicular distance from the axis of rotation to where the force is acting. So MA, mass of object A multiplied by G multiplied by dA, where dA is this distance, is equal to the combined mass of object B, C, and D multiplied by G multiplied by this lever arm. We solve, or we rearrange our equation and solve for mass of object A. We get this result. Notice the G's cancel. We plug in our masses, so we know that the mass of object C, D, and B is simply the combined mass of 0.25 kilograms. And what we're given in this square, so 0.75 kilograms plus 0.25 kilograms is simply 1 kilogram. So we plug 1 kilogram into this variable. We know what BCD is. Well, that's simply this distance. And we divide by dA, which is 0.3 meters. And we get that the mass of object A is 0.25 kilograms. So, mass of object A is 0.25 kilogram, mass of object C is 0.06 kilogram, and mass of object D is 0.19 kilogram.